Okay, well, let's start then. So, hello, I'm Algis Kalukas, and it's my pleasure to welcome one and all to the 8th in our free monthly virtual What Talk series. For anyone new, WHAT stands for Waterside Hypotheses, Aquatic Theories, or actually whatever you want. If you look at the logo, you'll see that there's some alternative words in there. Anyway, the idea in a nutshell proposes that the many peculiar physical differences between humans and chimpanzees are most plausibly explained by a more aquatic past in our evolution. So far in this series, we've heard from specialists from several fields, and I think most of the talks so far have been supportive or at least consistent with waterside models. If there are any that you've missed, please go to our website, whattalks.com, that's all one word, and watch the recorded videos. We have a primatologist, a malacologist, that's a specialist in mollusks, a nutritional biologist, a gynecologist, a social anthropologist, and a general practitioner. I did a talk too, although I'm not a specialist in anything, but I do have a PhD in hominid bipedal origins, at least to say at least that. Today, we add yet one more specialist to our growing list with Erika Schagatay, Professor of Animal Physiology from Mid-Sweden University, Östersund. Erika is an authority on breath-hold diving or freediving physiology. This is clearly an area of acute interest to those of us who think Homo sapiens had a more aquatic past. Erika first dipped her toes into this subject as a 13-year-old snorkeling in the Algarve in Portugal, but she soon progressed to scuba diving. It was a visit to the Red Sea that inspired her to become a marine biologist. Watching skilled freedivers there motivated her to get deeper into diving physiology by studying the human diving response. As a master's student, she tracked down a hidden tribe of divers, the so-called water people in Indonesia, and found they had a diving response in the range of semi-aquatic mammals. She found this puzzling for a terrestrial mammal until she coincidentally came across Elaine Morgan's first book, The Descent of Woman, which made it all make more sense. A keen freediver and instructor, Erika actually invited Elaine to take a freediving course with her, but she turned down the offer. "I like to swim," she said, "but I don't like having my head underwater." Sorry, that's my best Welsh accent. Since those early days, Erika's been pursuing a stellar career, researching and publishing on the human physiology of freediving, little of which was known when she first started. It would take half an hour to go through it all, but somehow I think you'd rather hear Erika. So let me finish by suggesting you visit our website for more information about Professor Schagatay's career and links to her vast published work spanning some 30 years. Before handing over, please remember to keep your microphone on mute for the duration of the talk. And if you have any questions that you want to ask her, why not enter them in the chat so I can put them to her at the end. Right, enough of me. So it now gives me great pleasure to introduce Erika Schagatay.
Thank you very much for this nice introduction. Is that all right?
That's perfect. Thank you.
If I hear. Yeah, okay. Thanks a lot. I'm going to talk about our own species' place among the diving mammals, which is what I have devoted most of my research career to, also long before I thought we were divers. And just a very brief overview of what I do. I'm a professor in animal physiology in a small university in North Sweden. We do breath hold diving physiology, but also high altitude physiology, where there is also a lack of oxygen. We do studies on pathological hypoxia like COPD and other lung problems, sleep apnea, and we also study temperature physiology. But my origin is from Lund University, where I was fascinated by the human tolerance to hypoxia during breath hold diving. This is my group. I have 3 PhD students currently. This is what we look like in the office. And this is what we look like when we work with the divers that we study. So we are quite hands-on in and on under the surface also when we measure things going on in the human body underwater. And of course, we work in the lab as well. What I'm going to talk about in this hour is why and how people breath hold dive. And what does it take physiologically to be a diver? And which abilities can you achieve by training? And the maybe most important question, can humans be called true diving mammals? First of all, breath hold diving, what does it mean? It has many names. Free diving is what I like most to use. And that is diving with just what's in the body, all the equipment that is inside your body and with no external air supply. It's often talked about under the name of apneic diving. Apnea means not breathing. And it can also be called natural diving because everyone can do it. Why do people free dive? Well, many people free dive as a recreational sport. So we will see some examples of that. It can also be done as a profession for obtaining food or other items that you live from. And it can be done as a competitive sport as well. Children like free diving, and I have 3 children, and together with them and their friends, I have started free diving schools in many places, and then I have continued training other people's children. And it is amazing to see how quickly and how eagerly children learn free diving. They basically love it, and they learn very fast. They even come with me to Norway, where the water is maximally 15 degrees Celsius in the summer, in August, where we do diving camps just for watching the underwater life. And also grown-ups train free diving because they find it an amazing sport. Most people over 18 years of age, they learn how to breath hold for 3 to 4 minutes or to swim 50 meters horizontally, about in a pool underwater, and vertically they can dive to 20 to 30 meters of depth within a year of training. Most people learn that in just half a year of training if you know what to train. And this is amazing because most people that start free diving training, they have no idea that they have these skills. What can you use it for? Well, as a recreational diver, you can, of course, go a little bit deeper and see a little bit bigger fish if you're a well-trained diver. So many people, they do it for going on holidays to Australia or other places to see the amazing big fish. This is a whale shark. This is taken in the Red Sea. A trained recreational free diver has a range between 5 to 20 meters of maximal depth. And then you can swim around for a minute or 2 with these amazing big creatures. Okay, the next category that I want to cover is professional free divers. And there are many, many examples all along the middle of the planet where the water is sufficiently warm that you can dive. And I will first take you to Japan. I have worked with professional freedivers called AMA in Japan in 3 different places. I have visited them for 4 different periods. And what they do is they dive for shellfish. This is a picture from a woman in Nanasojima outside of Wajima in western Japan. And she's diving here at around 10 meters of depth, collecting shellfish. You see she's holding one in her left hand, and she's kind of going along the bottom to find more shellfish. They have done so for at least 2,000 years. There are old historical records of AMA divers being important food catchers already 2,000 years ago. And they are still proudly do so. What they catch mostly now is the awabi, the abalone shell, and the sasai, the turbo shell, which they sell to Tokyo restaurants for a lot of money. Of course, there are a few middle hands also that make money in this trade, but this is one of the most important and expensive sushi for the Japanese culture. We wanted to know how they work underwater, so we connected some depth time loggers on their waist. You can see that on these 2 divers. It is a little capsule that logs everything that happens during a working day. And these are some examples of what we get out of this. We have here recordings from one AMA woman who is diving. She's 79 years old. Maybe you are surprised about that, but there are even older divers that are still active, because this is a trade that you can do up in high ages. The elderly diver, she's going to 3 to 4 meters, and she's resting quite some time on the surface, so she's diving about 1/3 of the time. Lower panel shows mid-aged woman, 61 years old, going to 8 to 9 meters in the same way. What we wanted to know was, in average, how much time do they spend actually working underwater? And this is a result of measurements on 14 AMA divers of different ages. And we found that they make short dives of approximately 40 seconds, and they rest a very similar time. You see, these intervals, they mean dive and rest. You have here dive, rest, dive, rest. So we recorded 10 dives of each diver, and this is the average. So they can work for 50% of the time they spend in the water, and they can obtain a considerable catch of these mollusks in this time. We also wanted to know, because we were amazed that some of the divers that were still active were really elderly. For instance, Sote-san, who was now 97. We wanted to know if age is important to the performance underwater. So we compared about 45 women, different ages. The youngest one and the oldest ones are the ones you see in this picture. Also this young lady that started this profession at an age of 18. And what we found was, here you see the groups that we used: under 35, everyone, above 36, but up to 45, 45, 55, 55, 65, etc. And the purple column is the group over 75. And you see we have 5 or 6 or 7 divers in each category. This is just showing mean diving depth, but we have measured a lot of other variables, but I'm showing you this as an example. We could see that the beginner divers were not quite as good as the mid-aged 36 to 45-year-old divers. But then there is a plateau, and not until you pass 75 is your ability diminished. And what does diving depth say? Well, there are bigger and more shells at a greater depth, so that the women, they want to dive to their maximum sustainable diving depth to get more catch. This is why they dive, to get some catch to sell. So we think diving depth, we also have a similar comparison with diving duration and swimming speed and all kinds of things. But there is a plateau from when you are fully trained until you are about 75 years old, where you can perform well underwater. And I think this is striking because I'm a professor also of sports physiology, and this is very unusual for physical performance, that you keep your ability for this long. Now we're going to another group of divers, and this diver group I encountered when I was doing my master thesis on something that I found very interesting, which was the human diving response. They live in Indonesia, Philippines, and Malaysia. And here are some regions where they are living. They're always a minority because they live as sea nomads, and nowadays they have settlements on the sea where they are diving for sustenance. These are some of the locations I have visited across the years. These are what the guys look like. These are the men that are spearfishers mostly, and we do physiology studies on them. They dive with only goggles. They usually don't have any other equipment, and they have extraordinarily big feet. Actually, we have a study on that now that isn't published yet. And they catch fish, but they also collect all kinds of edible things underwater. Here are the goggles exposed by one of the good divers. They make them from wood with a small round chopped piece of glass before the eye. This is from 1988, where I first traced down these populations. It took me about 2.5 months of travel before I found them. This is a story in itself, but I will not spend time with that. But then they lived still on houseboats. So many of the families, they lived on a little boat where they migrated between different shallow reefs where they could find a good catch. But the government in Indonesia didn't like nomadic people because they couldn't keep an eye on them. There was unrest in the country, in the islands. So they forced them to settle. And when they settled on the sea. So they have this kind of stilt houses. You see there is a stairway leading down to the water where they have the boat, and then they go again on the sea and in the sea fishing. So nowadays in Indonesia, most of the population of Bajau, they live in this kind of stilt houses. I studied their physiological diving response. I'm coming back to what that means. And I found that they have a tremendously strong diving response that conserves oxygen to the most vulnerable organs, the brain and the heart, when you hold your breath. And this is very similar to what you see in seals and whales. I just show you this picture briefly with the family of the chief Husimang from Topa village in 1998. This is me visiting the same people 26 years later. And even I will flip back that this little girl and this little boy are now grown up, those two, brother and sister, and father and mother, and all their children and grandchildren. I know them since many decades back. The population that we are so interested in, they are then everyday diving to between maximum 5 to 20 meters. Of course, they can dive to 1 and 2 meters as well, but there is not much catch there. But they can dive to about 20 meters regularly. And we are logging their dives. You see there is this little kind of drop-like dive computer that is showing what they are doing. And they are diving between 2 and up to maximum around 9 hours per day. So they spend a lot of time in the water. Here, this man, he's watching big fish in the deep water and waiting for a good way to harpoon a fish. He has a sling harpoon. What we recorded was quite amazing. It was that they can stay 60% of the time underwater. So they breathe for very short times. This is just an example of the recording. So they have a quite good working time underwater. If we compare to the AMA divers, you see there the rest intervals are shorter than the dive intervals. And here is both for the Bajau, the water people, and the AMA, the percentage of the time spent underwater. They can do this because they keep every dive very short in duration. If you try to dive for a long time, you have to spend even more time on the surface recovering, because then you get lactic acid produced because you have to go into anaerobic metabolism. I will not go into that too much, but I will just stop by saying that it's very, very clever to make many short dives instead of making one extended dive. So when you talk about human diving ability, it's not very interesting how long one dive can be. The interesting part is how much time of your working day can you spend on the seafloor, where the food that you are after lives. So if these people work for 9 hours in one day, 60% of the time underwater, they have 5 hours spent underwater, under the surface, without breathing, working, which I think is quite striking, especially if we consider ourselves terrestrial animals. This is an example of the women that are also diving. Here they are collecting seashells. So it's not only fish that is nutritious underwater, but very many people live from collecting seashells at a quite shallow depth. You don't have to dive to 20 meters to find them. Usually it's enough with 1 to 5 meters. Here's an example of where they are swimming. And also the children are good divers. They can even catch fish with their hands. And you see on the boy to the right that he is wearing no goggles. It's common for the children to not have the goggles yet, because they have discovered that they can still see quite well underwater. The boy to the left, he has a small sling, just a rubber band with a small kind of arrow that he can shoot fish with. But the boy to the right, he caught it with his hands. So you don't have to have a lot of tools to catch fish, and especially, of course, not to collect the clams. I was fascinated that these young children seem to see well underwater. And I got the attention from a vision research group in Lund University, where Anna Gislén later did a study on the Bajau, or on a very related group, the Mokwen in Burma. It is a very similar lifestyle in this group. And she found that they can actually accommodate underwater by constricting the pupil, which is opposite to what we normally do when we come underwater, where the light is less. Then normally our pupils dilate. But she could see, she could measure that they can see twice as sharp as we do underwater. And of course, we see a little bit blurry underwater. They see sharp enough to catch animals underwater, but still the adults, they use small goggles to see even sharper. So our vision is not perfect underwater, but it's pretty good compared to what we normally think. Okay, the third category of freedivers that I want to cover is competitive sports. There are many of them: underwater rugby, underwater hockey, like team sports underwater, where you hold your breath when you are allowed to touch the puck or the ball. Synchronized swimming, as in the picture, where usually ladies hold the breath and do amazing performances upside down in the water. You have to have a very good control of breathing, and also control of how you spend your oxygen to do this. In swimming, breath holding is important. When you turn, you're allowed to swim underwater, which is less resistance than on the surface, and many swimmers are good at that. You have spearfishing, where you also have competitions, and then you have the sport of competitive apnea. Apnea means holding the breath, and the sport where maximal apnea is the goal is called also apnea. This is just an example of the athletes that participate. This is the Swedish team in 2012 that was competing in the World Championship. So this is an ordinary sport where you have national, regional, and world championships every year. And the competition is done in several disciplines. This is an example of static apnea, where you are just breath holding underwater. And think for a second on how long you think the world record is. For how long can you hold your breath? I will put it on. World record is 11 minutes and 35 seconds. When I started to be interested in this field, I read in a lot of medical literature that the brain will die after you held your breath or were out of breathing for 5 minutes. But nobody that can hold the breath for just 5 minutes can compete in the world champs, because the qualification durations are much higher. And there are several people that can hold the breath for over 8 or 9 minutes, and a few over 10 minutes. And this is, of course, when you train to do this. But this is showing that we have a capacity that is kind of hidden in our body, where if we train, we can hold the breath for quite a long time. But remember, again, this is a different kind of task than being underwater for the full day for collecting clams. This is a kind of emergency thing. This is the maximum. Then there is a sport called dynamic apnea, where you train and swim in the pool horizontally for maximal distance. World record, again, is amazing, 300 meters. If you're a good breath hold diver, maybe you can do one turn in the 25-meter pool, then you swim 50 meters, so you can calculate how many turns you can make. It's quite amazing to see these performances. At this time, there are 3 men that have done 300 meters, and 1 woman has done 250, I think 260 or something like that. And these records are increasing constantly. And then you have competitions for maximal depth. Again, this adds another type of stress to the body, with compression of the air cavities, like your lungs and your middle ears, and everything is affected when the air inside them shrinks when you are exposed to the pressure of the water. Still, the maximal depth for diving vertically with a fin is 130 meters. And of course, they have to swim up again. This is done by muscle force, which I think is very striking for a terrestrial animal. Very strange. So if we very quickly review the 6 different competition disciplines that exist, the white numbers are for men, the pink ones are for ladies, and these are the world records. There are 2 different disciplines with the horizontal swimming in a pool with a fin. You see this woman has a monofin, and breaststroke. This guy is gliding, he has no fins on, so he's making very slow breaststrokes and gliding between them. And then there are 3 disciplines going deep. 1 swimming down and up with a fin, 1 swimming down and up without fins. And the 3rd discipline is where you are allowed to touch the vertical line that is guiding the other divers with your hands, and you're pulling down and pulling up again. And you see the amazing depths that the people have reached. Without fins, people have now reached beyond 100 meters of depth. And these records are increasing year by year, because more people discover the sport and discover a hidden talent to produce well in this sport. It's not like football, where most people try at some point in life, or running or something like that. because only a few percent of people ever try free diving, but it is an increasing sport in all of the world with the number of participants. So, okay, the physiology behind this, what characterizes a successful free diver? This picture is very busy. I will not stay with it, but we have done several studies to see exactly what is important for breath holding during resting conditions, what is called static apnea, dynamic apnea when you have to swim but not very deep, and deep diving. And I will not take you through the whole picture, but I have put a few rings of a few selected things that I will talk about. The human diving response that conserves oxygen, lung volume, where you have your storage of air, and blood conditions with the hematocrit, which is the oxygen-bearing protein in your red cells, and equalization techniques. I have posted with Algis some papers that are taking all the details from this for those that are interested. But let's start with what happens when you hold your breath. Normally, when you're breathing, you're doing that for two reasons. You get oxygen in, which is used in your cells, and you have to get rid of the CO2, carbon dioxide, that is kind of the waste product. So when you hold your breath, you have potentially two problems that you have to solve. This picture is basically showing the respiratory movements recorded with a string around the chest of a person holding the breath. When you start holding your breath, you don't feel an urge to breathe. This is called the easy phase. Here is where the breath hold starts. The person is breathing, taking a few deep breaths, breathing in and holding the breath, and it's very easy. It's called the easy phase. But suddenly, I think most of you have probably tried, and if you haven't, you should, just in the dry air, not in the pool. Hold your breath as long as you can. And then you feel suddenly that something is happening in your chest. Some people feel it in their belly. You get kind of a feeling. I have to breathe. This is called the physiological breaking point. And this is experienced like an inspiration that even if you have decided to continue to hold your breath, you feel your lungs are beginning to work. And that starts what is called the struggle phase. And this is where you have to consciously counteract your instinct to breathe. So this requires a great deal of voluntary control of your breathing, because if you were unconscious or if you were not really wanting to hold your breath, you would start breathing. But people can easily hold the breath for just as long time again after they feel that they have an urge to breathe. And this is requiring a great deal of voluntary breath control. And you see here, the person starts breathing again, takes a few big breaths, and then goes back to normal breathing. This is not a very long breath hold, maybe a minute and a half. But these points, this is the real breaking point kind of, and this is the physiological breaking point. They have helped us understand what happens when you, for instance, train free diving. What determines then your maximal apneic duration? Well, this is physiology. I hope you can follow, but I have tried to simplify a little bit. It is how much oxygen you can store, but also how much carbon dioxide you can store when you're not breathing it out. And this storage place is not only in your lungs, it's also in your blood and in your whole body, in your tissues. Second point is how low you can go in oxygen before your brain shuts off, because of course you have to surface consciously to the breathing situation. So the most interesting point is not when you actually should die from lack of oxygen. It is when you can safely surface after a dive. Asphyxia, it covers both low oxygen and high carbon dioxide, actually. And you have to have a tolerance to these two to surface in a healthy way. And the third one, I'm putting metabolic rate or the diving response. If you visualize them in a little bit different way, factor one is how high you can go in the storage of gases in your body. Factor two is how low is your tolerance. And factor three is what you do with it. What do you do? How well do you use the space between these two kind of physiological outer limits? Let's start with factor three, the diving response. This is a kind of visualization of the diving response that I like, and I use it in my teaching also. The left guy doesn't have a diving response. Blood is freely circulating all over the body. But to the right is what happens when the diving response kicks in. Blood flow is restricted to the central part of the body and the brain, and the skin, the extremities, non-working muscle, some internal organs, intestine, for instance, they are restricted from blood flow, or at least the blood flow is much limited in these regions. And this also means that the heart rate can be slowed down so that you have a much lower heart rate, even if you're working when you're underwater. Because the body that you have to circulate is much smaller. You don't need so much effect on the pump. And this also conserves oxygen because the heart, it needs oxygen to work. This is called in the technical terms vasoconstriction, peripheral vasoconstriction, where all the vases, all the vessels are constricted, and bradycardia, slow heart rate. This is one of the very original recordings I did on the diving response, which happens between the two blue lines in a 70-second breath hold. And this is the artery from the arm that you usually use for feeling your pulse with your fingers. And you can see here the radial blood flow is reduced directly as you start your breath hold. And it continues to be very low, the blood flow to the hand, let's say. And after you start breathing again, it becomes even higher than normal. And after a compensation, it goes back to normal here. Capillary blood flow, that is in the skin, this is measured on the thumb. It's also varying a lot always, because this is very fine-tuned for the situation. But when you start holding your breath, skin blood flow is reduced to almost zero. And then it evens out on a level that is much lower than before the dive, and certainly much lower than after the dive, when you have to compensate for this lack of blood flow in this period. So you have to pay back when these parts of the body have been restricted from flow. You are borrowing kind of the oxygen from the future, so you have to pay it back. This is also why you cannot breath hold for a very, very long time and then recover in a short time. Then it takes much time to recover. But if you keep the dive duration for about a minute at most, you can quickly recover from this. This is blood pressure. I will not go into that. This is respiration. Very high inspiration, and then you feel a little bit an urge to breathe. It begins to be some bumps here. And here's the most important, the heart rate, which is declining for about 30 seconds. And then it finds a heart rate that is good for the sustained apnea. This is what it looks like for a real dive. We measure now with monitors on the skin of the real divers. Here is a person going to 12 meters, not a very deep dive, for a minute. And his heart rate before going down is a little bit above 80 beats per minute swimming. Heart rate goes down, drops to about 34 beats per minute, goes a little bit up and down. It also depends on what you do, because here is swimming, so it's a little bit higher. And after the dive, you see here at 65 from 5, it goes up again and overcompensates a little bit and then you're ready to dive again in another minute. So this is the diving response. This is how you measure it. And when you measure it in different groups of people, I have measured here in professional divers. These are both the corresponding both to the AMA divers and to the Bajau divers, underwater rugby players, which are sports people, scuba divers that are used to being underwater and freediving a little bit, swimmers as well, and all kinds of non-divers and non-swimmers. You see that the diving response is much stronger in the people that are really trained for diving. Also, the apneic duration increases with these groups. We have seen in several studies, because we wanted to follow the same individuals to see if you can really increase your diving response by training. And we have found in these groups that, well, this is representing the heart rate. So this should be heart rate. And post-training during the breath hold, your heart rate is reduced more. So this is a lower heart rate after training. So it's quite clear that this is not an individual genetic characteristic of the person, but it is a response to training. So what starts the diving response? Well, we wanted to see which area of the face is involved, because we have seen that when you hold your breath, you have a small diving response. But when you dip your whole face underwater, you have a magnified diving response. This is the heart rate reduction, which is about twice as powerful when you have your face underwater. Skin blood flow reduction is also about 50% stronger when you have your head underwater. We found that from the sensory nerve of the face, the trigeminal nerve, it is the ophthalmic part, ophthalmicus branch that is covering the eyes and the front of the head that is involved. This is quite striking when you think of the diving response as a means of staying underwater efficiently for a long time, because it's only when you dip your airways underwater that you really need it. You don't want a diving response when you swim, for instance, like the left picture. If it was induced from the chins or the cheeks, probably you could still be breathing and swimming, and then you would have a diving response that would restrict blood flow away from your working muscles. But when you tip your head forward and wet the upper part and chill the upper part of your face, this is when you have a strong diving response. So this seemed very functional. And I was testing the diving response in simulated dives. That's when you dive with the head in a bucket in all different populations, and also in Indonesian free divers. It was found in mine and in other studies that the diving response is very sensitive to temperature. And it was said even to be strongest at 10 degrees Celsius. I thought that would be kind of useless for a tropical diver that dives in 25 or warmer degrees Celsius of water. So if this was true, it would not be efficient in a tropical diver. But when we tested that in a temperature chamber where we could have the air temperature of 10 degrees, we had another day of 20 degrees, another day of 30 degrees of air, and the subjects had to dip the face in 10, 20, and 30 degrees of water, we could see that when you had a very warm air temperature, even 20 degrees of water temperature would kick in, would make the diving response kick in. So it is clearly dependent on the difference between the temperature of the forehead before you go in and the temperature of the water. So it was not an absolute temperature requirement of 10 degrees. This was just when northern people, like in Sweden and Germany, were diving, that for their very cold air temperatures, 10 degrees of water was necessary to have the diving response elicited. So a Bajau diver like this man, he will also have a benefit from a diving response as long as the air temperature is even warmer than the sea temperature, which is almost always the case. Another observation that I think can be interesting is that this upper part of the trigeminal nerve, the ophthalmic branch, it covers much of the top of the head as well, not only the eyes and the forehead. And this is also where we are the least insulated with fat padding on our bodies. So this area, when you go to the surface, it really warms up very quickly. So the time you dive again, it will be chilled down, and it can be a kind of thermosensor starting the diving response. Peculiar is also that this is the place where men are balding when they get older. Maybe they get a much stronger diving response because they are bald. I wouldn't know why women are not balding then. So, but this is just an observation that this part of the head is very interesting from a water perspective of human evolution. About the diving response, finally, that we have shown, we have done long dives with the head underwater and the head in air, apnea in air, apnea underwater, 2-minute dives. And when you have a strong diving response triggered by immersing the head also, you have much more oxygen left. This is the white line. This is oxygen saturation of your blood than compared to when you are holding your breath above the water. So you see, it costs about half of the amount of oxygen when you're holding your breath with a strong diving response underwater. So this is showing that it's really powerful and working in man as well. So the diving response conserves oxygen. Okay, let's look now on storage. We know now we have a diving response that conserves the oxygen as much as possible, but can we do anything to store more oxygen and carbon dioxide? Well, you first probably think of the lungs. Oxygen supplies in the air-filled lungs is a very important part, but you actually have oxygen even a little bit more in your blood. So the lungs is just about half of your oxygen supply. And you have also in your muscles, in the myoglobin, a small oxygen supply that can be used by the muscle. And there are some other organs that are interesting in this respect. How long can this oxygen last if you do a maximal breath hold? Now looking at the kind of competition sport where you want to do one single very long breath hold. Oxygen consumption during rest, a typical number for that in a normal 70-kilo person would be about 300 milliliters per minute. And before your brain gets too low in oxygen, you can use up 50% of your oxygen, and then your brain decides to shut off. That is kind of the hypoxic blackout that can happen if you breath hold too long. But how long time can all these supplies of oxygen, which are about 2.1 liters in a typical person, how long do they last? Well, if you divide what you can use, half of that, with how much you need, you end up with 3 minutes, 30 seconds. So this is what we have in ourselves, most of us. But there is an individual variation, so you cannot count on this number for yourself, and you shouldn't try this underwater because you could be a person that is in the shorter range. But you can try this when you're sitting, resting in a chair to see for how long you can hold your breath. That's not dangerous. So a typical average person could hold a breath without problems for 3.5 minutes. And we are going to compare now the typical ordinary person to the trained diver. Here we have some values that we have measured on competition divers compared to ordinary people that are also athletic in other sports, 14 divers, 16 non-divers. vital capacity, that is the way to measure lung volume. That is when you inspire as much as you can and you exhale as much as you can. Their average vital capacity was 7.3 liters. And for other athletes that are non-divers, it was 5.5. So 1.8 liters larger lungs were found in the divers. And when you compare the divers among themselves, this was in the World Championship some time ago, you could see that the best divers, here are the total points in the World Championship. This is when you add up the points from the different disciplines of holding long time, swimming long duration, distance underwater, and diving deep down underwater. You see that lung volume seems to be important for your performance. Then the next question is are we made like that? And is it so that if you have large lungs, you become a good diver? So if you train diving, or if you try diving, you would discover that you have talent for it? Or is it an effect of training? We did a survey among the world-class divers and asked them, and they said, oh yeah, since I started training apnea diving, I have increased my lung volume by 2 liters or even by 3 liters, some said. And we said, how do you do it? And we interviewed them until we had a kind of set of maneuvers that they use that were common to very many divers. There was some variety. And we let some non-divers train this for 11 weeks. And these are the lung volumes before and after training in this group. And we also had a control group that didn't train, that it didn't change the lung volume. So vital capacity, maximal expiration, so to speak, was increasing in 11 weeks with about half a liter. So it's a lot that you can do with your lungs if you are dependent on them. So lung gas storage can be increased. What about blood gas storage, which was about half of your body gas storage? We wanted to know if the hemoglobin, which is the oxygen carrying protein in your blood, in your red cells, if that differed between divers and non-divers. So we compared very good free divers' blood hemoglobin to untrained people and also to other athletes, in this case, skiers that are common in Sweden. They are very well trained endurance athletes. But it was shown that the divers had a higher hematocrit and hemoglobin concentration. This is what determines how much oxygen you can store in your blood. So next, we wanted to know, is this an effect of training or are they just like that? We did a set of maneuvers that are also used by apneic athletes. And we had people hold the breath repeatedly 15 times a day. And this is the desaturation that you see in the arterial blood. Maybe it's too technical. But what we found was that the protein that is responsible for producing more red blood cells when you need them, for instance, when you are in high altitude, if you did this set of 15 apneas per day, this protein was increasing in the 5 hours following the training session. And this is showing that you can actually, by training breath holding, increase your oxygen carrying capacity of your blood. Then we have another funny story. And that is, we were starting to look at seals. And this is one of the very deep diving species, the Weddell seal. It eats stuff that lives on 500 meters. So it's better be very good at holding its breath. And it has been shown that these seals, they have a very high hematocrit when they dive, but they can store away the red cells in their spleen. So they can boost the blood with red cells during dives. And this is important for diving capacity as well. So we started looking at the human spleen, and the human spleen is kind of a minor volume compared to the seal spleen, but it still contains 250 to 300 milliliters of red cells, and they are just sitting there. It's just like a reserve. And what happens when you dive, this is showing how we measure it. We can measure it to visualize the spleen with ultrasonic imaging. And we can see, if you see in the upper panel, we can start across 3 dives, which are these blue pillars, that when we dive a few times in a row, like the Bajau and the Ama divers, the hemoglobin concentration increases. At the same time, the spleen volume, the lower panel, decreases. So if we make repeated dives, we can have the benefit from having a much higher oxygen carrying capacity in the blood than we do at resting conditions. And when you stop diving for 10 minutes, it goes back to normal, both of them. And we have done several studies. I think we have published about 15 papers on how this function really works, how it is initiated, and what kind of consequences it has, which you can read if you want. I will not go into that in detail, but it is very clear that we share with the seals the spleen blood boosting during diving. Here again, we compare between different competition divers. We see how many points they got in the total in the championships. And we can see that there are some that have a very high spleen volume, even much more than the normal. And of course, it's not the only factor that determines the performance. So there are also some good divers with a little bit average spleen. But what happens with these 3? Well, if you calculate how much extra oxygen they can store when they eject the red cells from the spleen, it's worth 30 seconds of breath holding, which is quite a lot in the competition sense. We compare them then with the competition divers that had the smallest spleens. So gas storage can in fact be increased by increased lung volume, increased hemoglobin concentration, and by spleen contraction. And can this be a result of training, or is it just like that? Well, we have seen that spleens are bigger in trained divers, but also studies have shown that if you train apnea diving, your spleen actually grows. So it's not only your lung volume that can be increased by training, it is also your spleen volume, and both of them help you to dive. So we are testing some of the best free divers in the world, and we can see that they can increase the circulating hemoglobin by about 10% when they squeeze the spleen. That is about half a liter worth of extra blood. We can also see that the Bajau, here I'm measuring with ultrasonic imaging. This is Dodi, one of the leading divers, one of the very skilled divers in one of the Bajau villages that we're working with. And he also has a tremendously large spleen. So for sure, we share with the marine mammals this spleen capacity when we are trained divers. So total oxygen after breath hold training can be increased quite a lot, up to from 2.1 liters to 3.2 liters. And oxygen consumption during rest, if we keep all of the numbers the same, we now end up with an ability to hold the breath, but we can still do something about the third factor, which is how low oxygen our brain especially can tolerate before we will faint from hypoxia. Let's first look at why we actually start breathing. It is not because of lack of oxygen. It is because of the CO2 rise. And this is a much more secure kind of system to tell us that we have to start breathing, because if already hypoxia would occur, then it would be kind of too late. The CO2 will rise much earlier than that. But divers can also use this to prolong diving, but they will also increase the risk that they come too close to hypoxia. It is by overventilation or hyperventilation just before they go diving. So little oxygen is added by doing so. That's when you take deep and high frequency breaths before going to dive. So the CO2 levels are lowered much, but the oxygen levels are not increased correspondingly. And I'm showing again this panel where you say there is an easy phase, and when CO2, carbon dioxide, is rising, you start to feel that you have an urge to breathe. And this is something good. This is what you have to know as a diver. So hyperventilation is absolutely not helpful for improving diving capacity. And it used to be in the kind of childhood of competition diving that people used a lot the hyperventilation to prolong the dives. But you also have to show after a dive that you are not hypoxic. You have to do a certain procedure to show that you are completely competent. And if you faint, you are disqualified, of course. So people have stopped using hyperventilation because they find that they can sustain the dive anyway. But coming back to this third factor, the asphyxia tolerance, it has been shown that if you do a lot of breath hold diving, you don't suffer from hypoxia at the same level of saturation of your blood as untrained people. So trained people, they can lose the consciousness at 30% saturation, while the normal is 50%. And also trained divers tolerate CO2 better. I will not spend more time on this slide because I see I'm already short of time. But this is also something that you can improve by training. So now if we can use after training up to 70% of the oxygen that is in your blood, you can already hold your breath for 7.5 minutes. And the metabolic rate, it can be further reduced by, for instance, yoga exercises and meditation and diet. I don't have time to go into that, but again, we can explain how people can hold the breath for up to 10 minutes. I will skip a few slides. This is showing that all of these factors that are affecting the limits, how much oxygen you can store, how much hypoxia you can tolerate, and how well you can conserve it. All of these are responsive to training, and you don't have to train very much to improve your own capacity. And that is quite striking because compared to other sports, freediving is recruiting a lot of people that discover a talent that they didn't have an idea of. So as I mentioned, we can now explain that people can actually hold the breath over 11 minutes with the measurements that we have done on the elite divers. So from an ordinary person to when you are a really trained diver, you can increase your ability by several steps for a maximal apnea. But again, the most important for a diver is not to hold the breath for a very long time once. I think it is to be able to work underwater. And let's go back to that. The successful diver has all these things in storage for being productive, and so do the professional divers. Large lungs, large blood volume, extra red blood cells in spleen, high tolerance of asphyxia, and a low metabolic rate due to the diving response. And when you see the development of this sport of apnea, you see also that the records have increased in not so many years, from 6 to 7 minutes to now 11:35. It seems like it's leveling off because this is already quite old record, but the human diving breath hold capacity in only one maximal dive is around 10 minutes. And this is, of course, well sufficient for deep diving. This is a picture of Sarah Campbell, a British freediver that she took on freediving from being a yoga instructor. She was a world champion doing 95 meters in depth after only 9 months of training. This doesn't happen in other sports. And it is quite common that people that start training freediving, they discover a hidden talent. But there is another thing that I want to cover before we finish that is needed to dive deep. It is equalization of the air spaces in the body, the sinuses in your head and your lungs. And it is an ability to divide where the air goes between your head and your lungs. And of course, you need also to sustain the pressure, so you need flexible lungs and you need a large and flexible tongue. When you dive down from the surface, already at 1 meter, your air spaces are compressed. And when you go beyond 1 meter, you will feel that you will have a kind of a click in your ears, like when you're landing with an airplane, that the middle ear is compressed and your eardrum is kind of pointing inwards, I would say. And this is because, according to Boyle's law, physical laws, pressure times volume is constant. So if you have here on the surface 1 atmosphere of pressure, that is all the air that is above your head, and you go only to 10 meters of depth, you will have another atmosphere of pressure worth. So you will have 2 atmospheres, and this means that your lungs will be compressed to half. So if you breathe in 6 liters, when you go to 10 meters of water depth, they will be worth only 3 liters, they will shrink. And you have to transport air into your middle ears and also your sinuses and everything else that is containing air. We are coming back to this. This is a very challenging situation for a terrestrial animal, but it's something that people have figured out. This is a picture just showing these air spaces in your head and in your lungs, and sometimes in your intestine, but that is not as important. So you have to know what to do with the air in your, especially middle ears and your lungs. Luckily, we have a very strong and flexible and extendable kind of downwards tongue. And the part of the tongue that is very important for accomplishing this is the back part and the opening that is made possible by your descended larynx. So if you compare to a chimpanzee, this part is what makes it possible to equalize the pressure when you dive down more than 1 meter or so. And the deeper you dive, the more challenging will be the equalization, that where you really need the root of your tongue to accomplish this. Here are some pictures. I don't think they are very good pictures. I wish I had time to draw new ones. I found them on the diving web pages. This is how you equalize hands-free using Valsalva, using Frenzel maneuvers. And if you go deeper, you also need mouth fill. You also need to use lung packing and reverse packing. And there are very many specific techniques where you have to train your tongue. And you have to train to feel what is your glottis and epiglottis and soft palate doing when you are diving. And in order to learn these equalization techniques, You are told to say specific letters. You see here, for instance, here is a diver that wants to overfill or pack the lungs with a little bit extra air after you have inhaled with negative pressure, full lungs. You can kind of use your tongue as a piston, like a bicycle pump, to press down air by opening your glottis and using your tongue and the back of the tongue exactly like a pump. And this is something that is necessary for deep diving, where you want to have a large lung fill to not reach the level where the lung volume is too small for your chest cavity to comply with. I know this is a little bit forced in tempo because I know I have too short time to show this, but here is how you are training to accomplish this. Here is also, you should say ko, you should say you should say repeat. If you want to know more about this, you can Google equalization, deep diving equalization. I didn't put a film because it would take too long. Efficient breathing and efficient equalization is essential for free diving. Here is another picture of a Bajau diver coming to the surface. And what you have to do after the dive is, of course, to inhale very quickly, fully through your mouth. And here is also where efficient mouth breathing is necessary. As far as I understand, this is something that a chimpanzee or a horse or other animals could not do as efficiently. What determines maximal depth? These are the few last slides. Well, here we see again the effect of the Boyle's law. Total lung capacity divided by residual volume, this is what it means, determines where you can reach without any risk of negative pressure building up in your lungs, diving depth. So we are comparing two people, one person with large lungs, but with 2 liters of the smallest capacity of the lungs. He can go to 30 meters without problems. Here we have another person, maybe a woman, with 5-liter lungs. Smallest lung volume when you exhale completely is 1 liter, and she can go to 5 atmospheres, which would be equivalent to 40 meters. This is the squeeze-free depth. That's when you can dive without any problems of pressure. But you see, if this person could squeeze down 1 more liter to start with, it would be 6 atmospheres required to go to the limit. So the same person as here could go suddenly 10 meters deeper. And this is why divers are concerned with lung volume anyway. So you could either reduce your residual volume or you could increase your total lung volume. And if you do this by intense training that we know works, a person that has a safe depth at 30 meters could suddenly go to 90 meters, which is quite amazing. And this is these are some pictures of the type of training that the people do. They do lung packing and reverse packing. They exhale and do a dive to kind of extend the negative side of the lung so that it shrinks more. And by doing so, people have been able to dive for more than 100 meters without fins. And this is only possible because we have all these physiological mechanisms in place. We have the diving response, we have the spleen contraction, and we have all these long-term effects of training that I have gone through. Human divers, they share several physiological features with diving mammals. The oxygen-conserving diving response, the blood-boosting spleen contraction, tolerance to hypoxia, especially from the brain after training. They have large flexible lungs that can sustain compression if you train them in the right way. And they have a very efficient way to equalize the ears and the sinuses and the lungs. So how good divers are humans then? Are we still terrestrial animals, or could we be even deserving to be called semi-aquatic animals? Well, the problem is that we are normally comparing ourselves to the excellent divers that have been for more than 50 million years evolving towards being aquatic, fully aquatic. Sperm whale can dive more than 1,000 meters deep. The beaked whale even much deeper. And humans, even when they use such a funny device to go down, they don't have to swim and they can just sustain the pressure. This is a record, but it's not a competition sport. That is called no limit diving. A person has come up after 214 meters of depth without any injury, but this is not something that you can use for sustaining your own living. It's just a very extreme maximum dive. But the problem is, I think, that most diving mammals, just like ourselves, cannot be compared to sperm whales or beaked whales or Weddell seals or elephant seals. So how far can we compare ourselves to other diving mammals? Well, if we put in the equation the 300 meters horizontal, more than 100 meters vertical, world record is 102, and being underwater 5 hours per day working. I think this ability is quite unique among terrestrial animals. And if you compare ourselves to diving species where the maximum depth and duration and the habitual diving underwater is known, you see that all these species, they fall down into 3 different categories. Deep divers are something very special. It's not so many species that are actually specialized in deep diving. As I said, the sperm whale and the Weddell seal are in this group. There are very many moderate divers. Here I'm showing just the maximal diving depths, but we have calculated a lot of other aspects of diving. But ourselves, we are typical of shallow divers. And shallow divers normally don't dive more than around 20 meters, and they can occasionally go down to around 100 meters. And there are several such species. And one is the sea otter. It's a quite large animal of the weasel family, and it can dive repeatedly down to 20 meters. It usually makes dives shorter than 1 minute, and it makes surface intervals of a little bit even shorter than that, very much like the Bajau, where they spend 60% of the time underwater. But occasionally they make very deep dives, exploratory dives. A few promille of the dives recorded in a group of these mammals were extraordinarily deep, but not more than 100 meters. So why do they do that? Maybe just to discover what is the situation outside, or I don't know if they have competitions and they press each other or something like that, but they have a very similar diving capacity compared to humans. Well, if we are like the sea otters, I have problems with evolutionary history of man. Why do humans have the same diving capacity as, for instance, the sea otters? Something I found very puzzling as a biologist, but when I heard by reading Elaine's first book, The Descent of Woman, about beach ape or waterside hypothesis, I said, oh, this is logical. There is a lot of food in the shallow water, and if our ancestors could for some period be dependent on it, we would have developed this kind of adaptations that I have been talking about. And of course, combined with the old arguments from Alistair Hardy and some very new striking evidence of air exostosis in fossil human remains and lots of shell middens in different historical and prehistorical populations, I think it's quite plausible that humans went at some point through a beach ape phase. And I was very excited when the publication from Pinnacle Point by Marian and company was presenting that some of the first modern humans left large shell middens at the eastern coast of South Africa, and also about all the research of how good seafood is providing our costly and large brains with building material for being smart. On the question, was man more aquatic in the past? I would say not necessarily. We are aquatic enough to live a self-sustained life from aquatic resources now. So modern humans, we have a functional diving capacity for shallow, and then I mean down to around 20 meters, efficient diving for a large part of the day. And we can dive from a very early age. I didn't talk about it, but Bajau, they used to give birth to babies in the sea. And I have seen small children from the age of 2 diving efficiently. And we know from the AMA that you can continue diving up to at least the 9th decade, which is quite amazing. So there are self-sustainable marine hunter-gatherers today that show that we are quite capable of living a semi-aquatic life now. Thank you. Sorry for the time taking. I was really struggling to shorten it, but I see I took more than an hour anyway.
Well, wow, that was fantastic. I've got about 1 million questions I want to ask. Are you happy to stay for a little bit to answer questions, Erika?
I can do that, of course. Yeah, sure.
Because that's fantastic. So, I'll just want to start off with one question, and then I'll throw the door open for anyone who's got a question. So if you want to put your hand up, I think Vernon's got a question. Maybe, I don't know. Is that right? No. Anyway, I'll just ask my question, and then we'll go on from there. So, I'm very interested. You kind of did a division between the Bajau people and the sort of trained divers. I was just wondering, is there any evidence for the sea people to do any of these sports themselves? I mean, I would have thought Indonesia could win all the gold medals at diving if some of their guys who have actually done this for a living were trained as well. So they got the best of both worlds. And just one final point about the feet. You mentioned that they've got bigger feet. Is there any evidence for any genetic influence here? Is it purely, how could they have bigger feet if it was all training? So there you go. That's my question.
Yeah, I mean, the foot story is something that I didn't want to talk so much about because we want to publish it nicely. And I don't want to be, what do you call it, surpassed by the genetics people. But we have data showing that these populations have huge feet. And for sure, foot size is quite a lot genetically determined, but also training of the foot when you are not wearing shoes make it wider, not necessarily longer. So this is something we are working on right now. So you will probably see a publication on that within a year or so. About the Bajau, if they would try to dive very deep or very long during dives, I have, in the beginning when I was studying them, I also made diving competitions with them, just either underwater in the sea or even with the head in the bucket, because I was also curious, like you say, if they could produce very long dive durations. But I think to them, it is essential to interrupt the dive to optimize the dive duration very efficiently. So they were not producing longer dives than like 3 minutes, 3.5. This is something I can do. This is something I could train each one of you to do. And I think it's much more important to know when you have to breathe, to be able to dive again for sustainable diving. And also with a lot of semi-aquatic and aquatic animals, they never produce one long dive. This is very unusual, at least. But they want to spend much of the day on the seafloor. So this is actually a completely different type of aim for diving, that you can recover quickly, and that this doesn't require very much time at the surface. So I think this is, maybe I shouldn't have at all indulged into the free diving competition ability here, but I'm a sports physiologist, so this is also what I study, how to become a very excellent one maximal diver. But comparing to the sea otter, it was 1 in 2,000 dives that they do that is approaching 100 meters, and nobody knows what they do there because there's nothing interesting living there. It seems like they're curious and they can sometimes go, but most of the days they dive for food for 15-20 meters deep, and people that live from the sea, they do exactly the same. Well, so it's a misunderstanding that maximal single dive duration is very important. It's only important if you have to get your food from very, very deep depths, because then you have the transport down that has to pay off in the bottom time, and then you have to transport yourself back to the surface to breathe again. But if your food is living shallow, there's no need for long dives.
Right. Okay. Thank you. Okay, I've got Malgorzata. Do you want to go next? And then if there's anyone else would like to have a question, we might have.
Yes, gladly. Thank you very much. This was absolutely fascinating. I wanted to just make one comment, because I remember once a few years ago speaking with William Bond, who entertained the hypothesis that, you know, the women diving communities were much more widespread, maybe even in Europe, and you know, he referred to the mermaids and the singing. And when I saw that slide, when you show what actually the divers do with training their mouths to increase, sorry, I'm a complete ignorant here, but this looks to me very much like a singing exercise. So actually, I would think that this actually would be interesting. I would even wonder if Ama or Henyo people, or Bajau, if they entertain singing, because and I also know from my singing teacher, then this trained singer, and I would mean folk singer, like a world music, you know, like kind of primitive singing, not opera singing, is actually increasing their lungs. And she can see it on her, you know, basically on her clothes. So she says. So this was that struck me, because maybe, you know, maybe it would be interesting to. I don't believe anybody would research that connection, perhaps. But
Erika, do you want to answer that, Erika?
Well, I am not studying anything like their types of singing or so, but for sure both the Ama and the Bajau, they have singing in their culture. But I couldn't say anything if this is specific or any more than other populations that I know are singing. Most human groups are singing. So, but it's very interesting. And I think also the kind of breathing, recover breathing that they use in the Ama and to some extent in the Bajau, but not as much, where they come up to the surface and they make noise that is kind of very specific. It is like singing. And I think it's very related to all the kind of training of your, not only your lungs, but also your tongue and your larynx system, and your somebody that is specialized in singing techniques should study these groups, I think.
I would think
Can
that.
you-
Yeah.
can
Thank you very
Leslie,
much.
can you
It was
go-
absolutely fascinating. Thank you.
Leslie, can you go next? I think you had a question.
Yeah, thank you. That was just fantastic. Thanks so much for that talk. Really, really interesting. I don't know if this was covered because my laptop ran out of battery and I had to re-plug it in, so I lost a few slides. But what I gathered about training was practicing holding your breath and doing the lung exercises. Is that the main way that people train to increase their capacity for holding their breath for, because you say it's 3.5 minutes, that's typical, anyone could be able to do it. I think most people would love to be able to hold their breath for 3.5 minutes. So what are your tips for kind of getting to that stage?
I think my simple advice is to hold your breath for as long as you can, 5 times a day, and rest and breathe between them for 2 minutes. This is the model that we have used in several training studies, and you increase your ability in a couple of weeks easily. But I also would like to warn against training in the water, because if you are training underwater with maximal capacity, you should have some safety diver, and I recommend that you go to a diving school for that, because people have figured out that it's easier to hold the breath if you hyperventilate, and then you can hold your breath until you faint. And unless somebody take you up, then you can drown. So it's training in air, sitting in a sofa or so while you're watching the news, and hold your breath as long as you can. Then you breathe 2 minutes, then you hold again, and you will improve your ability by a physiological straining a lot in a short time.
Thank you. Alexandra, have you got your hand up? Do you want to ask a question?
Fabulous, thank you.
Alexandra next then, please. You're on mute.
Hi everyone, thank you for that talk, it was amazing. I just have a couple of comments and a couple of questions. So I've been a competition swimmer, and I would say that one of the ways that you can train yourself to use your breath for longer is to swim and to do more strokes on one breath. And you can also practice the kind of push off and breathing out over a longer period of time, and that helps you train your lungs. But it was interesting for me to see the free diving exercises, because I'm doing Bikram yoga at the moment, because I'm going to go diving in a couple of weeks. And the free diving exercises are part of the Bikram yoga sequence. So they're exactly the same. And one of the reasons you do yoga is to improve your control of your breath and breathing. But I'm a reconstruction sculptor, and I've been working on Homo floresiensis, and I got up to a certain point where I started to think that she was a swimmer. So I've broken down the sculpture that I'm working on, and I'm starting again based on sort of what I have come to believe about it. But I also have started to think that Boise and Cadensis, right back, are much more aquatic. And the big brow ridge that that is present on lots of archaic skulls, I've started to think that's about supporting an aquatic eye and air in the face. So I am about to plunder the Natural History Museum in London for their skulls, because I'm really interested in this idea. So that's what I'm starting to think, just from the perspective of a sculptor trying to make reconstructions. So obviously it's a kind of eccentric, unpopular opinion, but I do have the ear of some quite prominent anthropologists, and I've been writing to one today. And I'm going to go back into the museum this week and start looking at the skulls that they have on display, and start some sculptures just based on what I can access from public displays. And then I will go, poking around wherever I'm allowed in. But I really... so Go on.
Maybe if Erika could comment on that, and then if somebody else has got a point to make, we could. I just want to try and give everyone a chance, because we've been going for an hour and a half, and I don't want to take up too much of Erika's time.
Yeah.
You want to just answer
Alexandra, when you say air in the face, do you mean that the eye ridges would be like a diving mask, which is something that occurred to me?
Yes, I think there's pockets in the face, because, you know, trumpet players fill up their faces. And I've just been wondering about that, because I really think that the prominent brow ridge is something about air. So, yeah, I'm not sure. I've just started to think it. So what do you think?
I have thought about when you dive and you don't see very clearly, if you hold your hands like this and you exhale a little bit, you get a mask, a cyclope. You get good vision. I noticed that when I was a child already, and I thought everyone knew it, but I have, you know, then I have thought that these big eye ridges, maybe they would do it for you, but I'm not sure. And I thought that was what you were talking about.
Well, I'm not sure, but thank you. Amazing.
The thing I would say about that is that chimpanzees and gorillas have got very, very huge
I know. Yeah.
Brow ridges, and I don't think we would think they were swimming and diving. Has anyone else got a question? Does anyone else want to make a point? Oh, it's gone silent now. Oh, it is me panicking, trying to get as many questions in, and of course now it's all fizzled out. Well, if anyone wants to ask another one, I mean, I've got loads that I want to ask. I don't want to take up too much of Erika's time. How long have you got, Erika?
It's no problem. If you have questions, I will stay. It's a Sunday after all.
Well,
I could ask some more.
Francesca, your turn. You have a go.
Okay, although I don't know how closely connected it is, or if Erika has an idea about this, but it just crossed my mind. Somewhere in the slide I saw she had put up, Erika, you put up something about high altitude and the connection. I wondered if have you considered it, is there any connection? You know, they say they found in the genome of some Tibetans higher Denisovan, and they obviously have they're better adapted to living in high altitudes. And I wondered if there could be any connection between the Denisovans, perhaps in the past, being more divers, and then because they've also spread, of course, to other parts of the world, in the Pacific and so on, islands. Could there be a connection there with their ancestors being divers?
I think so, yes. And we are writing about it. I have a PhD student that finished just a few weeks ago. He's now in Nepal. But we are doing a lot to see if the human diving ability on the individual level predicts your high altitude tolerance. And it does. I have a few publications I can post with Algis with this. I don't know what kind of platform you have, Algis, but I sent 3 reviews, but I skipped everything about high altitude. But you are right. I am more and more certain after 15 years of study in the high altitude. And I think it could even be that the same genes in the Bajau and in high altitude populations, and possibly in the Denisova, would be responsible for the hypoxia tolerance. And it being, if it is like that, which we don't know, I would say it's much more likely that they come from diving origins, because there is food in the water and there's scarce of food in the high mountains. It's tough to live there. So this is something. Are you working in genetics or?
No, I'm just have an amateur interest in our aquatic ancestry.
Yeah,
and I'm researching.
No, yeah, but I'm waiting for people with a genetics toolkit to look for these specific genes. And of course, it's a range of genes. It's not like 1 or 2. The study Ilardo that showed that the spleen size in the Bajau, we were working on that, and they had a publication that said it's completely genetic, but we have seen in the Sherpa population that it is an effect both of genes and of training. So I don't agree completely with that nice study that they did on the Bajau, but there are so many other aspects, including the foot size and everything, that deserves genetic study. I don't know if I answered your question. I'm just.
You did, actually. Yes, thanks very much.
I just wanted to say, yeah, thanks. Erika sent me 3 papers, 3 PDFs, and when I do the video and put it online, I will make sure that those 3 papers are on the website as well, so anyone can download. And if you have any others, Erika, I can put those.
I can select. I mean, I published around 100 papers on this, but I can select another 5 or so that I think are relevant to this discussion, and I can include some of the high altitude, which I thought was not kind of in the scope now. But it is striking that the same features that make people good divers seem to make people good high altitude people.
I mean, I put a link to Erika's university webpage, and the reference list just goes scrolling for pages. I think there's more than 100 there, but I'll put a few PDFs on the website itself as well. Has anyone else got any other questions? Has anyone got any questions? Humphrey, you want to go? You go next.
Yeah, you were talking about the graphs of the depth of diving by the AMAs relating to age. Do you have an idea of, was their lung capacity gone down, or you don't know?
We did a study that was published in '96 on, it was actually, that study was on male AMA, but we looked at the vasoconstriction and the bradycardia, and it seems like even if there are Japanese that they eat a lot of health food for our conditions, they get stiffer vessels. So they have a bit slighter ability to vasoconstrict and to reduce the heart rate. So they have a weaker diving response with age. But otherwise, it seems for the depths that they are going and for the durations of dives, that it not much happens before they are over 70 years of age. I was expecting them to be best between 20 and 40, like in most sports, but they seem to be equally productive until they are in the 8th decade. So this is something that would, I mean, with the aquatic ape hypothesis, explain how we live so long, but we are crap runners when we are 50. I mean, but we are very excellent divers when we are 75.
No, that's right. Yeah, I mean, I love that point you said at the end there, you know, that we're actually very aquatic now. You know, it's not so much the question, were we aquatic in the past? From studying this for 25 years, I've come to the conclusion that I believe, it's just my personal opinion, that we were at our most aquatic when Homo sapiens first emerged, and we evolved on the coast of Africa, and that's where we became really as good as we are today, really, with a bit of training. And the stuff you did on the face, I mean, that's fantastic. That it's the temperature difference that causes the bradycardia, and the fact that it's all of these nerves around the forehead which seem to be key, because the forehead has got the highest density of follicles in the body, and yet it's pretty much glabrous. And I think that's a really key. There must be something there, and you mentioned about the baldness as well. That was really fascinating. I really love that one. So, sorry, I'm rambling. Does anyone else want to say a final question? I think we should really wrap it up because we don't want to go on. We could go on all night here, but it's been really fascinating. I loved every minute of it. I've got pages of notes that I would like to ask questions, but we obviously just don't have time. And does anyone else want to make another question or point? And then I think we should close it. Okay, well, in that case, can I just say thank you very much, Erika. It's really great. Thanks for giving your time. And it's wonderful talk. Thank you.
Thank you,
Thank
Erika.
you very much. Thanks for listening.
Thank you.
If you have questions, I can answer them in the forum or on email. So just
can I put your
just
email,
forward it to me.
Can I put your email on the website?
Sure.
Okay, thank you.
You can.
So if anyone's got any extra questions they want to ask, feel free to do that. Well, thank you very much, everyone. Thanks for coming. It's been another great talk. And so next time, hopefully, we've got Peter Rees-Evans, who's going to talk about the paranasal sinuses. So that's kind of related to what you were talking a little bit, at least. And the ear exophyses. That's going to be interesting. So divers. Yeah. So thank you very much, everyone. And I'll see you next month, hopefully. Thank you.
Yeah. Thank you. Bye-bye.
Bye-bye.
Bye-bye.